Welcome to this introduction to the electromagnetic spectrum. Today, we'll explore the complete range of electromagnetic radiation, from radio waves to gamma rays. This is a fundamental concept in understanding how light and energy travel through space and interact with matter around us. The electromagnetic spectrum is the complete range of all types of electromagnetic radiation, spanning from the longest radio waves all the way to the shortest gamma rays. Despite their differences, all electromagnetic waves share the same fundamental nature. They all travel at the speed of light in vacuum, which is approximately 300 million meters per second. However, they vary significantly in their wavelength, frequency, and energy levels, which gives each type its unique properties and applications. Every electromagnetic wave has three key properties. First is wavelength, represented by the Greek letter lambda, which is the distance between consecutive wave peaks. Second is frequency, represented by F, which tells us the number of wave cycles that pass a point every second. Third is energy, represented by E, which increases as the frequency increases. These properties are mathematically related. The speed of light equals wavelength times frequency, and energy equals Planck's constant times frequency. Understanding these relationships is crucial for understanding how different types of electromagnetic radiation behave. Let's begin with radio waves, which have wavelengths greater than 1 meter and frequencies less than 300 megahertz. Radio waves possess the longest wavelengths and the lowest energy in the entire electromagnetic spectrum. Their main characteristic is their ability to travel long distances and pass through various materials. Radio waves are extensively used in broadcasting television and radio programs, in communication systems like cell phones and Wi-Fi, in astronomical observations, and in radar systems for detecting objects and measuring distances. Next, we have microwaves, with wavelengths ranging from 1 millimeter to 1 meter and frequencies between 300 megahertz and 300 gigahertz. Microwaves are shorter than radio waves and have a unique property. They are readily absorbed by water molecules, which makes them perfect for heating food. Beyond cooking, microwaves are essential for satellite communication, radar systems used in weather forecasting and air traffic control, and wireless internet technologies like Wi-Fi. Moving to infrared radiation, we find wavelengths between 700 nanometers and 1 millimeter, with frequencies from 300 gigahertz to 430 terahertz. Infrared is most commonly experienced as heat. All warm objects emit infrared radiation, which is why we can feel warmth from a fire or the sun without touching them. Infrared has numerous practical applications, including thermal imaging cameras that detect heat signatures, remote controls for televisions and other devices, night vision equipment, and heating systems. Now we reach visible light, the only portion of the electromagnetic spectrum that human eyes can detect. Visible light has wavelengths ranging from 380 to 700 nanometers. This narrow band contains all the colors we can see, from violet at the shortest wavelength through indigo, blue, green, yellow, and orange, to red at the longest wavelength. Each color corresponds to a specific wavelength and frequency. This rainbow of colors is what allows us to see and perceive the world around us in all its beauty and detail. Beyond visible light lies ultraviolet radiation, with wavelengths between 10 and 380 nanometers. Ultraviolet has higher energy than visible light and is invisible to human eyes. One key characteristic of ultraviolet radiation is that it can cause fluorescence, making certain materials glow. However, it can also damage DNA, which is why excessive sun exposure is harmful. Despite this danger, ultraviolet has beneficial applications in sterilization and disinfection, detecting counterfeit money and forged documents, and helping our bodies synthesize vitamin D from sunlight. X-rays are high-energy radiation with wavelengths between 0.01 and 10 nanometers. The defining characteristic of X-rays is their ability to penetrate soft tissue while being absorbed by dense materials like bone and metal. This property makes X-rays invaluable in medical imaging, allowing doctors to see inside the body and diagnose fractures and other conditions. X-rays are also used in security scanning at airports and in crystallography, which helps scientists determine the structure of molecules and materials at the atomic level. Finally, at the extreme end of the spectrum, we have gamma rays with wavelengths shorter than 0.01 nanometers. Gamma rays possess the highest energy of all electromagnetic radiation. They are produced by radioactive decay of atomic nuclei and by extremely energetic cosmic events like supernovae and black holes. Despite their danger to living tissue, gamma rays have important applications in cancer treatment, where they precisely target and destroy tumors, in sterilizing medical equipment, and in astronomical observations that reveal the most violent events in the universe. Let's review the complete electromagnetic spectrum in order. Starting with the longest wavelengths and lowest energy, we have radio waves, then microwaves used for communication and heating, followed by infrared, which is thermal radiation. In the middle is visible light, the only range humans can see. Beyond that is ultraviolet, which lies beyond violet light. Then come X-rays, which are penetrating radiation, and finally gamma rays with the shortest wavelengths and highest energy. It's remarkable to realize that all these different types of radiation are actually part of one continuous electromagnetic spectrum. They're all the same fundamental phenomenon, just with different wavelengths and energies, giving them vastly different properties and uses in our world.
If you like this video, hit that like button and don't forget to subscribe. Visit codelucky.com for more such useful content.